provide the culvert width equal to the width of the channel, then we are probably contracting at that point. Similarly, in the bridge also, bridges are normally made narrow than the actual width of the channel, and so that sort of situation for providing sluice gate also, we narrow down the channel width, then we provide for a particular portion the gate. So for all those situations there is a contraction of the channel, and for that situation how the flow behave. Well, let us first see what we did. We did in the last class that we covered that jump, how the jump can be classified, that we could see. Then we were discussing about height of jump and about length of jump, how we should measure this height and length of jump. We should try to do it as precisely as possible, and it is difficult in laboratory also. And then we were starting a discussion about the energy loss, how the energy gradient line suddenly drop in the hydraulic jump portion, and on the upstream of hydraulic jump, if we neglect other loss, then head loss is neglected or quite insignificant. At the downstream of hydraulic jump also head loss is insignificant if we consider this to be that friction loss and other things are negligible. And but in the portion of hydraulic jump, all forms of loss will be coming, and that way the significant loss of energy will be there, and a hydraulic gradient line will drop suddenly at that point. Well, we will start with that today. Then of course we will be discussing on efficiency of jump by when we are talking about a particular device, because jump is, now we can say it is a device that we use for our various hydraulic design, in our hydraulic structure for various purpose. Then what is its efficiency? When we talk this as a device, then we need to know what is its efficiency. So that we will discuss. Then location of jump we have discussed to some extent, that we will again review just briefly. Then stilling basin I did mention in the last class, but still in the previous class I did mention, and that again we will just see. And then we should know one point, that what we are discussing here or what we are discussing in this particular class is not all about hydraulic jump. There are some other issues that are related to hydraulic jump, and we should know our limitation, that we have studied up to this much and we need to study something more about that. Okay, that will do. Well, so how we can calculate the energy loss, that let us see first. Say this is the hydraulic jump, and this is our upstream section 1 and this is downstream section 2, and we are just giving this as y1 and y2, and say velocity is v1 and here it is v2. And again, if we consider this as a rectangular section, then our expression become simple. Otherwise, of course, we can always find for different section also, just to have in a simple form. Say in rectangular section, what we can do, say energy loss EL is equal to E1 minus E2, and E1 minus E2 is nothing but say Y1 plus V1 square by twice Z minus Y2 plus V2 square by twice C, or that we can write as Y1 minus Y2. And so for V square by twice Z is concerned, that we can write as, say, V square is nothing but Q square divided by Y square. So what we can write, Q square by, say, okay, let me write this twice Z here, and then this expression can be written as, say, y1 square minus y2 square minus y1 square divided by y1 square y2 square. Okay, just writing v1 square minus v2 square, that if we bring it in this form, then it become 1 by y1 square minus 1 by y2 square, and that if we just summarize, we can write it in this form. Well, now this particular expression q square by twice z, if we recall our earlier discussion, for that we can write in a different way, that is, say we were writing in this expression starting from this one, say P1 minus P2 is equal to rho Q then V2 minus V1. That is our very basic momentum equation, neglecting the other friction loss, and then considering this as rectangular, we can write half of, say rho G H1 square minus half of rho G H2 square, and this is equal to rho Q. That Q part, as we are, of course we are talking about unit width, here we are writing H1 square, B we are neglecting because B is prismatic, and that is why here also we can talk about unit width, so we can write Q directly. So that will be, actually we can write rho and then Q is equal to, say V1 and Y1. So we can write V1 Y1, and this we can write as, okay, our target is to obtain Q, so let me keep Q here, and we can write it as Q remaining here. This V1 we can write as Q by Y2 minus Q by Y1. Okay. Now this part we can write as rho will get cancelled, G will be going there, 2 we can write here, so we can write it as, say H1 square minus H2 square, this is equal to twice Q by G, and then this Q bringing out we can write Q square by Z, and then that will be, say Y2 Y1, and this is Y1 minus Y2. Well, here we are using Y, so this H would be actually Y. Then what we can have, that is equal to Y1 minus Y2 into Y1 plus Y2. This is equal to twice Q square by Z, and Y1 minus Y2 divided by Y1 Y2. Now this we can say that this Y1 minus Y2 and Y1 minus Y2 will get cancelled. So this will implies that twice Q square by Z is equal to Y1 Y2, that Y1 Y2, here it is Y1 Y2, Y1 Y2 into Y1 plus Y2. So using this relation, twice Q square by Z is equal to, this is the relation, that Y1 Y2 into Y1 plus Y2. Now here we have a term Q square by twice Z, but this term is twice Q square by Z. So just replacing that part, what we can write, say Y1 minus Y2 plus, in this this will be Y1 square Y2 square, and then this, as 2 is here, to have another 2 there we will have to multiply it by 4 and divide it by 4. So we can write it as 4 here, and then this will become twice Q square by G, and we can replace this by Y1 Y2 and Y1 plus Y2, and this term we can write in the form that Y2 minus Y1 into Y1 plus Y2, Y2 plus Y1 or Y1 plus Y2, the same thing. And now from here, if we bring Y2 minus Y1 common, Y2 minus Y1 if we bring common, then this term will become, say minus 1 plus 4 Y1 square Y2 square, and then this part we are bringing Y2 minus Y1, so it is remaining as Y1 Y2 and Y1 plus Y2 whole square, Y1 plus Y2 whole square, this Y1 plus Y2 and this is Y1 plus Y2 whole square. So now by simplifying that, this Y1 Y2 and this square term will go. So what we can write, that is Y2 minus Y1, and this expression will be, say 4 Y1 Y2, this will be minus 4 Y1 Y2 plus Y1 square, this if we break then plus twice Y1 Y2 plus Y2 square, and ultimately if we simplify that part, then this is becoming y2 minus y1, and then this part is y1 square plus y2 square, and this 4y minus 4y1 plus 2y1 y2. So, this will become minus 2y1 y2. So, this expression will become y1 minus y2 whole square divided by 4y1 y2, and that is equal to y1 y2 minus y1, this you can write y2 minus y1, y2 minus y1 whole cube, this square and that one. You are writing y1 minus y2 whole square or y2 minus y1 whole square, same thing. So, y2 minus y1 whole cube divided by 4y1 y2. So, this expression is very popular expression for finding energy loss. Let me write down here now that energy loss is equal to, we can write, or if we have space on the next place, let me see, we can write energy loss EL is equal to, we can write y2 minus y1 whole cube divided by 4y1 y2, where y1 is the depth before jump and y2 is the depth after jump, or these are the sequent depth of hydraulic jump. So, this is one of the important expression for finding energy loss. Well, then what is efficiency of hydraulic jump? As hydraulic jump is being formed for, in many cases we do it for dissipating energy. So, let us see how we observe or how we view the efficiency of that particular device. Well, if E2 is the energy after the hydraulic jump, that is here say y2, and this energy level here is E2 and energy level here is E1. Say if I draw the energy gradient line, then it is going like this. So, this E2 is the energy here and E1 is the energy here. Then the ratio of E2 by E1, E2 by E1, and that is basically called as efficiency of hydraulic jump. Now, if we just write it in terms of energy loss, then what we can do, that this expression say efficiency, we can write efficiency is equal to this. So, now how we can write this? If we calculate the energy loss, that means why we are writing all this expression, say energy loss we can directly calculate as a function of y1 y2 directly. So, we may not calculate this E2. So, without calculating E2, if we just calculate E1, then also we can write this is equal to say E1, and this E2 can be written as E1 minus energy loss, or we can write 1 minus say EL by E1. So, that way also we can calculate the efficiency of hydraulic jump. This is one expression and this is one expression. I mean, if you are not calculating, or if we are not calculating the E2, then we can, and we are calculating suppose energy loss directly from this one, then we can calculate it in this way. Well, then another topic that is of importance is location of hydraulic jump. As we have discussed, location of hydraulic jump, say on the downstream of a say dam where the hydraulic jump will be occurring, that is very important, that we have already discussed. And if the tailwater depth we can control, if this tailwater depth we can control somehow, suppose it is low, tailwater depth is low means it is getting repelled and it is jump is occurring here. So, location of hydraulic jump, where it will occur, how we can determine? Say we are having this y2 dash tailwater depth we have, and first we need to see if this flow is supercritical. At upstream flow, if it is supercritical, then only hydraulic jump will be forming, and at downstream of course we will have to have subcritical flow. Now, if the corresponding is suppose y1 is this one, then we can calculate the sequent depth y2. Now, if we find that y2 is not equal to y2 dash, that is the existing tailwater depth, and which is most commonly encountered situation, that calculated y2 will not be equal to the existing tailwater depth y2 dash. If your y2 dash is less than suppose this y2, then we need to find out where it will be located. So, how we can do this? That is, say we know this y2 dash, and so from this y2 dash we can calculate indirectly what is our y1 dash, that is this particular depth we can find out y1 dash. And now this y1 dash and this y1, between these two depth, this profile, if this is a mild slope, then this profile will be M3, and then our understanding of computing gradually varied flow profile is now coming into play. That is, we know that in this M3 profile our upstream depth is y1 and downstream depth is y1 dash, and so from here to here now we can compute the M3 profile, and this will give us the length of M3 profile. This length of M3 profile now we can calculate. This is the length of M3 profile. Of course, if our channel is horizontal, then we are not talking about M3 profile, and in that case we are getting H3 profile. So, whatever profile we are getting, but with our knowledge of gradually varied flow, we can compute that particular profile, and then we will be knowing the length of that particular profile. Suppose this length of that particular profile is say L1. So, this L1 once we know, then from this point where we are observing the y1, then we need to add this L1, and this will give us the location of this hydraulic jump. And then what will be the length of hydraulic jump? Now, that also we know from the height. If height is this one, say height of this hydraulic jump is equal to now y2 dash minus y1 dash. So, length will be equal to say 6 times of this y2 minus y1. So, this will give us the length of that hydraulic jump, length of hydraulic jump. This is equal to say 6 times of y2 dash minus y1 dash height of hydraulic. So, that way we are getting this length also. So, from this point, to what extent the jump will be, to tell the phenomenon of jump will be, that we can say that L1 plus LHJ. So, that way we can know location of a hydraulic jump. Well, just knowing the location may not help us in our practical purpose. So, what we need to do is that as we were discussing earlier, if the jump is getting repelled by significant length, then the work that we need to carry out for protecting the bed from this high speed supercritical flow, we need to spend a lot of money, cost is involved there, and that way we need to do something so that we can contain the hydraulic jump just on the foot of this say spillway, or just on the downstream of this spillway, so that we can avoid taking protective measure for a very long distance, and we can contain the jump here. For that purpose, we use certain devices, and that is called say stealing basin. In fact, for different Froude number, different type of stealing basin has been suggested. Different type of stealing basin has been suggested for different value of Froude number, and that way in this particular course we are not going into detail of those things, but basically in those stealing basin, what is that? Say it will be a basin of this sort, and here we provide some say like this. Okay, if I draw it in a 3-dimensional view, we can draw it in this form, that at this end we provide a height like this. Okay. At this end we provide a height like this, and then here we are providing some block of this sort. We are providing some block of this sort. Well, and some more blocks are there, of course, and these blocks are called soot block. These blocks are called soot block. That means I can just put an arrow. Then in between again we can provide some baffle block. This we can provide some baffle block like this, and of course this shape can be different. This shape can be different like that. We can have some baffle block place here. Several baffle block we can place. Now, well, I am not drawing that in detail, and then at the end we are providing some seal like this, and this is called seal, and these are in between whatever block we are providing, that we are calling as baffle block. My diagram is not that proper here, but anyway, these are some concrete block that we are providing to obstruct the flow, and then flow is moving. There are cross current forming, and that way this energy get dissipate here, and this seal actually it here the water depth rises, and that way it helps in forming the hydraulic jam within this portion, So that portion is called sealing basin. And what is dented seal? Sometimes we do not provide a continuous one, and with some gap we provide. Say one seal is up to this much, then another seal is there is gap, some portion we leave. So that way when we leave some portion, then we call this as a dented seal like that. Say this portion is seal, this portion is seal, again this portion is seal like that, and some gap are there, some opening are there here. Okay. So this sort of seal are called dented seal. And now in some, for very low Froude number, we may not be requiring this baffle block, we may not be requiring this soot block, and then say with increased Froude number, I mean this combination of these things we can change. In some of the sealing basin for dissipating high energy we need all these, and in some of the sealing basin we do not require all these. So that way the sealing basin is one device which is used for dissipating, or which is used for definitely for dissipating energy, but main purpose is that energy will otherwise also get dissipated, but here we are trying to contain the hydraulic jam very near to the downstream of this structure. Suppose this is our dam or something which is here, so and water is coming like this, and this we want that I mean the hydraulic jam to form in this part. So this is one sealing basin. Details of that of course we are not discussing in this particular class, and then we need to give special consideration to some of the issues, like that when we are talking about a jump in sloping channel, like this, then if we measure the depth in this direction y, then actual flow cross section in this direction, so our this will be y cos theta, y1 cos theta, and that will also be y2 cos theta, because our basic concern is that we are measuring the pressure in the direction of flow. Similarly, when we are neglecting this w sin theta, if the slope is quite significant, theta is significant, then we cannot neglect this w sin theta. So w sin theta will be playing its role, that is weight of the fluid is coming here, and similarly this depth we need to consider as y1 cos theta, y2 cos theta, and that way we will be getting a different expression. Now details of that we are not doing here, but at the same time we should be aware of the fact that the relation that we are using y2 by y1 is equal to half of root over 1 plus 8f1 square minus 1. That particular relation is of course valid for rectangular, but for a situation where our slope is almost 0, that we are neglecting the slope. If slope is there, our expression will be different. In place of f, we will be having another term capital G, which is popularly used, and then this will involve these term. This will involve this term. Well, then if the channel is in a, if the jump is occurring in an expanding channel, this expansion can be, say, it can be like that. It can be like that. When the jump is occurring in expanding channel like that, then also this expression that I am using, or we are using rather till now, will not be directly valid. There will be some other terms coming. Similarly, expansion may not be that sharp, it can be a gradual expansion like this, channel in a gradual expansion. Well, then sometimes this hydraulic jump can occur in a situation where we are just dropping the channel bed. Suppose the flow is coming and jump is occurring from this part, and depending on this depth, jump can occur from this level. So that way, for all those different situations, we can have hydraulic jump, and the equation that we are using will not be directly applicable. So for those situations, we should go for further study in this particular topic. Well, not very critical, or not very it is nothing like that, it is very difficult, but anyway, we should be aware that the expression will be little different. Then jump on non-rectangular channel, that we have of course discussed, that if it is not a rectangular one, if it is a trapezoidal one, then our this Ballinger's momentum equation will not be valid, and in that case we need to start from specific force, equating specific force at upstream and downstream side, and some graphical solutions are there, some empirical solutions are there, observed, and then some equations has been derived, but of course those are applicable for some limited situation, but these things are existing. And otherwise, using a computer, we can just use the trial and error procedure for calculating the depth of downstream based on the depth on upstream, or either way it can be based on the condition that specific force at upstream and specific force at downstream are equal. Well, so this sort of understanding is required, so that with our limited knowledge on the hydraulic jump, what we have done, we may not end up doing mistake in using those equations directly in this different sort of situation. Well, then let us start our discussion on a topic, that is when flow in a channel passes through a narrow section, when the flow passes through a narrow section, that is channel width is reduced, when channel width is reduced, how we can how the flow profile will change, and what sort of care we should take in those situations. Well, now if our channel is changing like this with some smoothness here, I am drawing the top view, and in plan view of course it will be suppose slope is not changing, or neither bed is changing, say the same slope is there, and then, well, let me not draw this one right now, slope and other things are not changing that much, but the width is contracting. Now in this situation, the friction loss, as this portion is very small, the friction loss within this portion can be neglected, and that is why once we neglect this friction loss, and of course form loss can be considered neglected if it is smoothly changing, and then the energy loss between this upstream, say this is E1, and energy at E2 can be considered to be equal. That is, energy loss between this upstream and downstream section is negligible. Now when we consider the energy loss to be negligible, then we can analyze this sort of flow by using our equation. If we remember that when we did discuss about specific force, then we were talking about specific force diagram, and we were talking about specific energy diagram, and also we were talking about depth discharge diagram. And that depth discharge diagram, if we recall, that we could get a curve which was for a particular level of energy. For one energy level, we got one depth discharge curve, how it is varying. So those curves we can use, and using those curves we can analyze the flow in this situation. Of course, our basic assumption is that energy loss we are neglecting between these two sections. Well, now let us see, first let us draw that particular curve. Say if we talk about rectangular channel, then we can write it as unit discharge Q, and suppose we are putting the unit discharge Q here and depth y in this direction. Then what we mean by depth discharge diagram, that it is coming like this. It is coming like this. This is the depth discharge diagram, and this line we are getting for a particular energy level E. Say this is for energy E, specific energy E. For, I mean, along this line our energy is remaining same. When energy remains same, then with the increase of depth, discharge is changing, or we can say when discharge, unit discharge is changing, then depth are changing. Again, this point is critical depth. This point is critical depth. So once we know the critical depth, then we know one more point, that depth above critical depth is subcritical, and this is supercritical. Then we know another point, that well, with the change of unit discharge, depth is changing, that is of course obvious, but if the flow is in subcritical zone, then with the increase of unit discharge, you can see that curve shows, with the increase of unit discharge, depth is decreasing. Depth is decreasing. When your Q is increasing in this direction, depth is decreasing. And if you are in supercritical region, then with the increase of unit discharge, your depth is increasing. Say Q1 is this one, Q2 is this one. When Q1 is greater than Q2, when Q1 is greater than, sorry, Q2 is greater than Q1, Q2 is greater than Q1, then we can see that this is Y1 and this is Y2. So what we can see, that Q2 greater than Q1 means Y2 less than Y1, Y2 less, sorry, Y2 greater than Y1 in case of supercritical flow, Y2 greater than Y1 in case of supercritical flow. Here Q2 is increasing, Y2 is also increasing. But if I extend this line to subcritical zone, then we can see that for subcritical zone, this is the Y1 and this is Y2. So Y2 is less than Y2 for subcritical zone. Now, with this understanding, then now we can try to analyze the situation when our flow is changing through A, when our flow is passing through A with or contraction, channel contraction. So here our B is B1 and here B is B2, well, and Q coming is Q, fine. So unit discharge Q at this point is Q by B1, and at this point is Q is equal to, I can write this as Q1, this is as Q2, this is equal to Q by B2. So as B2 is less, so Q2 is greater than Q1. So what we are having, that Q2 is greater than Q1. Well, now what about the flow depth? if the channel is like this and suppose a subcritical flow is coming from this side, a subcritical flow is approaching. So, it is coming like that, and in this narrow portion, normally we have a feeling that when our depth is say when our width is reducing, width of the channel is reducing, then depth will increase, because width is reducing, Q remaining same, we have a feeling that okay, depth will increase, but this is not true for this situation. You can see that Q2 is greater than Q1. So, we are in subcritical region. So, if our energy loss is negligible or we neglect the energy loss in this portion, then what will happen? What we will be having, that when Q1 is when our say in this diagram, of course, our Q1 is smaller. So, Q1 will be this one. Let me draw another curve. This was just to explain the understanding of this particular curve. Now, if we just use the value, here, say this is my y1, where Q is this one, we are talking about subcritical flow. So, this is the y1, and this is the y2, Q1 is this one and Q2 is this one. For this sort of situation, we can see when discharge Q1, unit discharge Q1 here is less than the unit discharge Q2, that means it is the situation of this kind. You can refer the diagram. Q1 is less than Q2, Q1 is changing from Q1 to Q2. When Q2 is increasing, depth is changing from Y1 to Y2, that is, depth is reducing from Y1 to Y2. So, if our flow depth here is coming as a depth Y1, here at this section the depth will be reducing like that, So, it will be coming as a, of course, smooth curve, and depth will be reducing like that. So, this depth will be Y2, and that sort of situation we will be getting when we contract this channel, and this is for, of course, subcritical flow. Now, if the flow is supercritical, then what will happen? Now, you can see that in supercritical, suppose other things remaining same, say if the flow coming is supercritical, let me draw it here just below this one, say flow coming here in this section is supercritical. So, it is coming like this, and in supercritical flow, for Q1 the depth is Y1, this one, and for Q2 depth here is Y2. So, what we can see that when our Q2 is increasing, Y2 is also increasing, and that way for supercritical flow, if depth here is Y1, then depth will rather at this point it will rise and it will be moving like this, and this corresponding depth will be Y2, and Y2 is greater than Y1. So, this is just reverse. In subcritical flow the depth is falling down, and in supercritical flow the depth is depth is rising. That is one phenomenon what we can see. Now, say another situation we can have here is that suppose we are reducing the B and we are reducing it to a point such that this B2 is corresponding to the critical depth. What we mean by that? When we are reducing the B, with the reduction of B, our Q is increasing. As you can see, Q is increasing. And then for a particular B value, this Q will become QC, our Q will become QC. That means we are arriving at this point. Depth is coming down and depth is coming down, and we are getting a depth which is critical depth. This is our YC. So, we are getting critical depth at this point. So, we can reduce it up to a particular B value, so that we can get a critical depth here. Fine. Now, the point is that, well, we can get critical depth by reducing it to a certain width, but if we reduce our width beyond that value, what will happen beyond that value? Suppose we are reducing it further, say we are reducing it further. Now, beyond BC, if we reduce, what will happen? Well, it is coming down, and then for BC value, this correspond to depth YC, for this is for BC, bed width is equal to BC, we are getting this YC. And then if we reduce it further, then our Q will increase more. But we, in this particular curve, which is for a energy level E, we cannot have a point, or we cannot have a higher discharge than this QC. This is the maximum possible discharge that can pass through this particular section with energy E. So, but our discharge is more than that. Our discharge is more than that. Then how this will negotiate? But in the real field, it will definitely stop. It will definitely not stop. It will not stop. It will rather keep on flowing. But something else will happen, as this energy level is not sufficient to push the flow through this small narrow width. So, what will happen? Energy level or water will start impounding on the upstream side, so that the energy level increases. So, in fact, this indirectly will allow the water to impound upstream, which will make the energy level higher at the upstream, and that higher energy level will push the water through this narrow portion. And diagrammatically or graphically, what we can say, that for a higher energy level, we will be getting another curve. For a higher energy level, we are getting another curve like this. And this line is another depth discharge diagram that we are getting, another depth discharge diagram. Let me draw this depth discharge diagram. What is requiring me to rub all this part? That is because we are reducing the depth further. So, this energy level will be increasing from E to say E1, and E1 is higher than E. And at this higher energy level, what will happen, and to what extent it will rise? Because it is rising just to push the water through this point, and it can push the water when the depth at this narrow portion is again critical, up to critical. That is the maximum discharge possible here is critical at critical section. So, if our B has been narrowed down further to have the discharge of this much Q, nu Q, suppose nu Q, then our upstream will be rising. So, this will remain there, and the upstream will be rising like that. Upstream will be rising in this way, and this rise will make the energy level to increase here. Say energy level will be E1. Earlier the energy level was E here, earlier the energy level at this point was E, here it will be E1, and in fact this high energy level will push the water, but depth here will remain critical, depth here will remain again critical. Well, so that way we are getting again critical depth here, but this critical depth and this critical depth, there is a difference, but we are getting critical depth here. and at critical flow, or we can say the flow condition will be critical at this point, and but upstream it will rise. So, that is actually one of the very important phenomenon which creates problem in our engineering activity, because as we were discussing many a time, we require to narrow down, the width of the channel. But if we reduce the width up to a certain point, we can get critical depth. But if we reduce beyond that level, well, depth here or flow condition there will remain critical, but upstream side will be rising, that is, it will impound water in the upstream side, and that creates problem. Say flow velocity here will be reducing, and then there may be flooding on the upstream, that efflux will create different type of problem. And if we want to avoid this sort of efflux, suppose in a city drainage system, if we are talking about, say, in the main drain, just you imagine, say in the main drain, well, let me draw a diagram here. Say this critical width of contraction we are talking about, we have already discussed that part. Say the main drain is going like that, and there are lot of sub drain or sub channel which is contributing water to this main drain. Suppose we are talking about city drain, these are feeder channel, there may be feeder channel from different part, okay, buildings are there, and that way. Now say in this part somehow we have a breeze and we are narrowing down that width. Now if we narrow down this width, so obstructing that part, we are keeping this much opening and breeze is there. Why we narrow down the breeze? Because to reduce the construction, and sometimes suppose we are putting a sluice gate, that way also we may reduce the width, because if we try to cover entire portion by sluice gate, that is not possible. Huge gate will be there, operation cost will be there. So really we do not want that bigger size also, so we reduce this size, and then flow will be moving like this. Okay, flow is moving like this, that means it is just like the narrow section that we are making. And now if this width goes narrower than the critical BC, if this width goes narrower than the critical BC, then it will start impounding water in this level. Now if I draw the section, say here the water level will be rising. Now when water level is rising in this part, then say feeder channel are supplying water to this one drainage. So when water level here will be rising, then there will be no gradient from this side to that side, because water level here will be more than the water level here, and this water flow will also stop. That way this part will be having drainage congestion in this part. So for designing a gate at the downstream, suppose we are planning that we will pump the water or do something, then when we are, or in normal situation we will keep it opening, then while designing this sort of opening we need to take care, otherwise a flux will be there on the upstream and this may cause drainage congestion in other part. And just to see that mathematically how we can calculate the BC value. Well, again let me take this situation that we had one point that E1 energy at this point is equal to 3/2 of YC. If we remember that point, that when we were discussing our critical depth, then minimum energy E1 at critical condition, we can express this at 3/2 of YC. And of course, we are writing E1 because at the contracted portion, well, let me just take this diagram here. At the contracted portion, we are getting critical flow condition. At the contracted portion, we are getting critical flow condition. Here we are having critical flow condition because our bed width is BC, and at the upstream we are not having critical flow condition, but we are assuming one point that the energy at upstream E1, that depth is Y1 and energy level suppose E1, that energy and energy at this level is same, because we are from our diagram itself we are considering that energy loss is not significant. So, we can write E1 is equal to 3/2 of Yc. Now, what is Yc? That Yc we already know that Yc is nothing but Q by Bc, that is the unit weight, and square divided by G, that is Q square by G whole to the power 1/3. Q square by G whole to the power 1/3. And that is why what we can write that E1 is equal to 3/2 and cube root I am writing here, and this is equal to say Q by B whole square, because our known item is Q. So, I am writing it in this form, and our interested or we are interested in computing this BC. So, I am writing this as Q by B form. So, it is Q by BC whole square divided by Z, and then this expression can lead us to one relation, that is making Q, and then suppose we can make E cube, then we can remove this part, then it will be 3/2 cube. So, from that we can separate out BC, and this way if we simplify this expression we will be getting BC is equal to 3/2 whole to the power 3/2, 3/2 whole to the power 3/2, and then it is Q divided by root over G and E1 to the power 3/2, E1 to the power 3/2. So, we can get this expression, and further simplifying this expression we can write that BC is equal to 3/2 to the power 3/2, that will become 1.84, then 1.84 Q divided by root over G into E1 to the power 3/2. Again, what that E1 is, that energy E1 is equal to Y1 plus V1 square by twice C. Now, at upstream if we measure the Y1 we can always get this value, and of course, in some cases by neglecting the approach velocity we can simplify this expression further. That means, if we neglect the approach velocity, V square by twice G will become 0, and then we can take this as a Y1. So, that sort of simplifications are also done, but basically this is the expression for calculating BC. So, when we know the width of the section here upstream, B is known, B1, then we can calculate, knowing the B1 is, as we know the Q, we know the Y. So, we can calculate E1, and then we can see Q is known. So, we can calculate all this part, and then we can see what should be our BC. And if we want to have critical flow condition here, we should make the flow, make the width equal to BC, then only we can get critical flow condition. Well, then using this particular principle, that when we have critical bed width here, then we have critical flow velocity here and critical depth here, we have Yc here. Based on that, we can devise one flow measuring device that we call as a Venturi flume. What is the advantage of this? That suppose we narrow down, we know this Y1, and we narrow down this width sufficiently, so that this width sufficiently, we narrow down this width sufficiently to form critical condition of flow at this narrow point. Now, once we are sure that it is critical flow, then we can find out the discharge based on the depth of flow at upstream. Now, more important point is that to form critical depth here, we know that critical BC, but we can, if we further reduce this width, still the flow depth here will remain critical, upstream will only rise. And for measuring device, if upstream is rising, we do not have any problem. We want to get the discharge based on the measurement that we will be conducting at upstream point. And as such, what is that? We know this relation that critical depth is equal to q square by g and q whole to the power 1/3 or cube root of q square by g. Now, what we can do at upstream the energy E1 is equal to 3 by 2, again we can write cube root of q square by g, that expression. And then already we have written in the last page. So, similarly we can write that E1 is equal to say y1 plus v1 square by twice g, and 3 by 2 cube root of this q square I am writing as q by b2 whole square by 1 by g. B2 means this BC, we are talking at the section 2, B2. Okay. So, now here if we neglect this approach velocity, because depth will be rising sufficiently. So, velocity with which flow is approaching is almost negligible. So, neglecting approach velocity, what we can have, that is q, this term will become 0, and then by just rewriting this expression we can have a form that q is equal to 0.544 B2 g y1 to the power 3 by 2. Well, so with this expression, once we know the y1 value at upstream, then we can have what the discharge is flowing. So, in a channel, in irrigation canal, if we can have a ready-made system of the type that by that we will narrow down the particular portion, or we can have a permanent section where the section is being narrowed down, then just by observing the flow depth at upstream, not in the narrow portion, just at upstream if we observe the flow, then we will be in a position to say what discharge is flowing, and that is what is called Venturi flume, and this is used for flow measurement. Well, then like this narrow down, sometimes we can have a situation where this depth is raised, not depth rather, the width is raised. Suppose the bed is raised by delta z amount, then a subcritical flow is coming, then what will happen to this one? Say this is E1 energy, and at this point say what we can write, that E1 or E2 is equal to E1 minus delta z. Otherwise, there is no energy loss, that is why we are using, and as here we can use the relation our specific energy diagram. Here we can use our specific energy diagram, this one. Here we can see that at this point, suppose our energy level is E1, okay, at this point, and here hump is there. So, with respect to that, if we measure the energy, it will be say this minus delta z. So, if we reduce the energy by delta z amount, if we reduce the energy by delta z amount, then what will happen, that originally if our depth was this much, if it is subcritical flow, then it will come to this one. So, if y1 is the depth here, then y2 will be the depth here. So, depth is coming down. So, over the hump also depth will be coming down like this. But if it is supercritical flow, if depth was initially this much, then it will be rising like that. So, for supercritical flow, depth will be rising. If it is a supercritical flow coming, then a hump is there, then depth here is y1, then depth here will be y2, and then y2 will be greater than y1. And here if it is y1, this is y2. In case of subcritical flow, y1 is greater than y2. So, that way in case of hump also we can get this sort of a relationship. And here why we are using this specific energy diagram, because this diagram is for a constant q, and our q is not changing here, that means width of the bed is not changing. So, we are using a constant q, and then we can use this specific energy diagram to have these things. Now, here if this z is raised to a higher depth, suppose up to this much, if it is increased to delta zc, if it is increased to a critical depth delta ZC, then our flow depth will become critical. Z is coming here, so E1 will be coming down to E minimum. That is, we are having minimum energy or we are having critical flow condition. Then flow here will become, flow depth here will become say YC. Now, the condition is that if we further reduce this one, then what will happen? If we further reduce this particular level, then this energy level, because you cannot accommodate delta Z here less than that. So, what will happen? This delta Z will have to come here. That means total length will be increasing, rather energy level of upstream will have to come up. And with the increased level only, it can accommodate the delta G, which is delta Z, which is higher than the critical delta ZC. So, if delta Z is greater than delta ZC, that is hump height is greater than the critical delta ZC, then depth here will remain again critical, because after accommodating this part again we are coming to critical depth. So, depth here will remain critical, but the upstream level will rise. So, it is almost similar to the case of narrowing down, but of course, concept is little different, and we are analyzing this from the point of specific energy diagram for constant discharge. Of course, in case of supercritical flow, also we will be getting up to critical depth, it is fine. If it is increased to delta ZC, it is fine. But if it is increased further, then it will not. In case of supercritical flow, in case of subcritical flow, we are talking about that this depth is like that. In case of supercritical flow, when we are talking about this situation, then when delta Z is increased beyond these things, then it will lead to formation of subcritical flow in this part and a hydraulic jump will occur. So, in case of supercritical flow, a hydraulic jump will occur, and we cannot analyze this flow by using this particular diagram. Rather, the flow will be a hydraulic jump is coming, so entire flow situation is changing. Well, with this one, here we can conclude our discussion on flow over hump and flow over a narrow channel portion, and we have seen that how in critical flow and in subcritical flow the flow can be of different type, and for particular situation we can analyze it with the help of one curve and in a different, that is the depth discharge diagram in case of narrow down, and in case of hump we can analyze that by using the specific energy diagram. Thank you very much.